Okay, so we're going to address sampling distributions of proportions. So let's go through some vocabulary and terminology. Parameter, we're going to talk about the variables that are related specifically to parameters. Remember, parameters describe the population, parameter, population. These include mean, standard deviation, a proportion symbol, y-intercept of an LSRL, so that alpha, and then the beta, which is the slope of the LSRL. Statistic, which refers to a sample, again, statistic, sample. Let's see, and those symbols would be X bar, S for standard deviation, P hat, A and B. Okay, so we're going to talk about a distribution of some type. A distribution of a variable is simply a description of what all variables could show up in the sample. So we roll a dice, what do we expect to see, and then we go out and run the simulation a couple times. A sampling distribution is a set of all possible values from the statistic. So when we go out and we look at the sample, what possibly could happen within that population. So in the case of, say, flipping a coin or pennies, we would, look at what percent of the time did heads show up versus what percent did tails show up. And in this case, P would represent the population proportion of what the overall distribution would be. Now, we understand when you look at pennies, half of the time it's heads, half of the time it's tails. But when you start flipping coins, you're not talking a population anymore. You're talking a sample because you're actually physically doing it. And so in that sense, the definition of P hat is simply the fraction or the proportion of what is the observation divided by the total sample size. Okay, so we're going to do a little hypothetical here. Suppose we have 6 individuals: Alice, Ben, Charles, Denise, Edward, and Frank. A, B, C, D, E, and F on purpose. And we are interested in what proportion of our population is female. So this is called the parameter of interest. Okay. Now, given that population of 6 individuals, what percentage or what proportion is actually female? So of the 6, Alice and Denise are female. So that means 2 out of 6, or 1/3 of the actual population is female. Okay, and so then what we're going to do is we're going to, very simple case, we're going to grab 2 people out of the population. Now, I'm going to suggest we're going to do it at random, but really what we're going to do is we're going to write down every possible combination that could occur. So out of 6 people, 2 at a time, that's a combinations issue. That would be 15. Alright, so there's 15 different combinations, and I'm going to list them out for just a minute. There's Alice and Ben, Alice and Charles, Alice and Denise, Alice and Edward, and I can go on and just write down each individual list. Now, on your handout, you've got that chart with blanks on it, so that's what you can fill in, are just the letters that represent the names of the individuals. Okay, so let me go back to that list again. And in looking at each pairing, we're going to write down what percent of the time, or which of that sample, what percent of the sample is female. So at Alice and Ben, you got 50% female. Alice and Charles, 50%. Alice and Denise is 100%. And as we go through each of these pairings, we're just going to write down what percent of that particular sample is female. And then what we're going to do is you're going to go to your calculator and type all of those numbers into list 1 and do 1 var and calculate the mean and the standard deviation. Please take a second and do this. Don't just watch the video and write down the 2 numbers that I'm about to put on the screen, but actually practice finding the mean and standard deviation of of that set of numbers. So when you type it in, hopefully you got a mean of 1/3 and a standard deviation of 0.29814. Okay. Now, here's the question. How does the sample distribution of the pairs, the two people at a time, how does that mean of the sample compare with the mean of the actual population? And in the short sense, they're the same number. So the mean of the sampling distribution and the mean of the population would be the same. Now, this next one's probably not too obvious. What do you notice when you look at the standard deviation, or offhand do you notice anything? And that one's kind of a hard one to describe. Okay, we're going to do this again, but we're going to do it with sample size 3. So there's a nice lovely chart there for you to fill in the blanks on. I'm going to ask, before you watch the video further, see if you can come up with the different combinations. If we've got 6 individuals and we're looking at groups of 3, that's a combination 6 comma 3, which means there's 20 different ways. And so part of the challenge is trying to figure out what are the actual 20 different ways that could show up. So again, pause the video and see if you can come up with the different combinations. Okay, so there's the list of all 20 of them. You can kind of look and see if you got them all or if you were missing one, or hopefully you didn't come up with some extra ones. And then what we're going to do is we're going to go back into this chart and we're going to write down what percent or what fraction of the time do we have a female in the sample. So like out of A, B, and C, A being Alice, Alice is the only girl out of the 3, so that would be 1/3. A, B, D is Alice and Denise are the 2 females, and there's 3 people, so that's 2/3. So when we go through each of the pairings, we come up with that set of numbers. And we're going to go right back to our calculator. And we're going to type in that group of numbers into list 1, and then figure out one var stats, get the standard deviation, get the mean and the standard deviation. So the mean ends up being 1/3, and the sample standard deviation ends up being 0.2108. And so the question is, what do we particularly notice about the mean and the standard deviation? Well, hopefully we noticed that the mean was the same, whether it was sample size 2 or sample size 3. And then again, that standard deviation is a little tricky. What do we notice happened from the last time to this time? And hopefully you got the conclusion that it went down, got smaller, and it turns out there's actually still another pattern going on. Okay, so in a general sense then, when we're dealing with sample proportions, the formulas are the sample mean is the proportion of the sample, and the standard deviation, and this is a new one for us, this would be the square root of p times 1 minus p, I like to call that q, divided by the sample size, would tell us the standard deviation of our sample. Okay, now this is just a real quick technical side note. Please don't make a big deal of this. It turns out when we have really small samples like the ones we just had, the mathematics on calculating the standard deviation isn't quite right. Technically, you're not supposed to have sample size 2 or sample size 3. That's kind of ridiculous to go out in the population and only talk to 2 people. But there are formulas that allow for that typical thing, called a population correction factor. And so if we have a very small sampling distribution, we would use these formulas to kind of adjust our numbers. So using our formula, we end up getting a standard deviation let's see, of the 1/3, 2/3 over 2 of sample size, we end up getting this number, and that's not quite right for the overall population. So if we take that continuity factor into account, meaning if we'd sampled more than just 2%, then we would have gotten sort of the correct number. Okay, now this is just a theoretical concept, so I'm not going to test you on that particular statement. So just FYI, in case you're wondering, how come the formula didn't give us 1/3? Again, take the continuity factor into account, it does. But it does bring up another assumption that we need to double check when we talk about population. In order for our sample size to be large enough to do this sort of analysis, we need to make sure we have at least that our population is less than 10%. So if it's less than 10%, then we don't violate this continuity rule. Okay, so sum up the rule, the assumptions, and then we'll jump into some examples. So first assumption is that the sample size needs to be less than 10% of the population in order for these calculations to work. And on the same sense, the sample size must be large enough to make sure that we have a normal approximation. And we've seen those formulas before. That's NP greater than or equal to 10 and N times 1 minus P greater than or equal to 10. Okay, and again, this is a little side note just to remind us. When we looked at binomial distributions, we talked about comparing a binomial to a normal. If we had a very skewed distribution, we would have to have a larger sample size to guarantee that the sample distribution is normal. If the probability of success was closer to 0.5, then the sample size didn't necessarily matter. So point being, when we talk about being normal with these samples, we just need to make sure they're large enough. Okay, so other than the theory about why that all works, what I want you to walk away from are just these two statements. Remember that sample size has got to be less than 10% of the population. That's an independence rule. And that NP and N times 1 minus P have to be bigger than or equal to 10.